Machine Learning for Trading book aims to show how machine learning can add value to algorithmic trading strategies in a practical yet comprehensive way. It covers a broad range of machine learning techniques from linear regression to deep reinforcement learning and demonstrates how to build, backtest, and evaluate a trading strategy driven by model predictions. In 4 parts with 23 chapters plus an appendix, it covers over 800 pages. Important aspects of data sourcing, financial feature engineering, and portfolio management, the design and evaluation of long-short strategies based on supervised and unsupervised machine learning algorithms, how to extract tradable signals from financial text data such as SEC filings, earnings call transcripts, or financial news, using deep learning models like CNN and RNN with market and alternative data, how to generate synthetic data with generative adversarial networks, and training a trading agent using deep reinforcement learning. The book's website contains chapter summaries and additional information. Join the ML4T community to make it easy for readers to ask questions about the book's content and code examples, as well as the development and implementation of their own strategies and industry developments. We are hosting an online platform. Please join our community and connect with fellow traders interested in leveraging machine learning for trading strategies. Share your experience and learn from each other. What's new in the second edition? The second edition demonstrates how you can extract signals from a diverse set of data sources and design trading strategies for different asset classes using a broad range of supervised, unsupervised, and reinforcement learning algorithms. It also provides relevant mathematical and statistical knowledge to facilitate the tuning of an algorithm or the interpretation of the results. The second edition also covers the financial background that will help you work with market and fundamental data, extract informative features, and manage the performance of a trading strategy. The ML4T workflow starts with generating ideas for a well-defined investment universe, collecting relevant data, and extracting informative features. It then involves designing, tuning, and evaluating machine learning models suited to the predictive task. Finally, it requires developing trading strategies to act on the model's predictive signals, simulating and evaluating their performance on historical data using a backtesting engine. Once you decide to execute an algorithmic strategy in a real market, you will find yourself iterating over this workflow repeatedly to incorporate new information in a changing environment. Installation, data sources and bug reports. The code examples rely on a wide range of Python libraries from the data science and finance domains. It is not necessary to install all libraries at once because this increases the likelihood of encountering version conflicts. Instead, install the libraries required for a specific chapter as you go along. Updates include the availability of various ML libraries on Conda Forge, the removal of Docker for newer zipline versions, and updated Conda environments for recent Python, Pandas, and TensorFlow releases. To run the notebooks, download and pre-process many of the data sources used in the book. If you have any difficulties installing the environments, downloading the data or running the code, raise a GitHub issue in the repository. The repo also provides data such as Algorithmic Tr market data and daily equity data for backtesting. Outline and chapter summary. Part 1. From Data to Strategy Development. Chapter 1 explores industry trends that have led to the emergence of machine learning as a competitive advantage in the investment industry. It examines how machine learning fits into the investment process to enable algorithmic trading strategies. Chapter 2 shows how to work with market and fundamental data, describes critical aspects of the environment, and demonstrates how to use Python to access and manipulate trading and financial statement data. Chapter 3 outlines categories and use cases of alternative data, describes criteria to assess the growing number of sources, and summarizes the current market landscape. Chapter 4 discusses financial feature engineering, how to research alpha factors, and how to generate data using wavelets and the Kalman filter. It also covers testing alpha factors with zipline and evaluating predictive performance with alphalins. Chapter 5 covers portfolio optimization and performance evaluation. It describes how to measure portfolio risk and return, manage portfolio weights using mean variance optimization and alternatives, use machine learning to optimize asset allocation, simulate trades with zipline, and evaluate performance with Pyfolio. Part 2, Machine Learning for Trading, Fundamentals. Chapter 6 introduces the machine learning process, covering supervised and unsupervised learning, training, tuning, and evaluating predictive performance while addressing overfitting, cross-validation, and time series considerations. Chapter 7 explains linear models for regression and classification, including linear regression, logistic regression, regularization with ridge and lasso, and how to use them to predict stock returns or directional price forecasts. Chapter 8 presents the end-to-end ML4T workflow for designing, simulating, and evaluating a trading strategy driven by a machine learning algorithm. It covers planning backtests, avoiding pitfalls, choosing vectorized versus event-driven engines, and using Zipline or Backtrader to create strategy prototypes. Chapter 9 focuses on time series models to forecast volatility or create statistical arbitrage strategies. It covers autoregressive and moving average models, arch and garch for volatility, Victor autoregressive models, and co-integration for pairs trading. Chapter 10 discusses Bayesian machine learning and dynamic risk measures such as dynamic Sharpe ratios, dynamic hedge ratios, and synthetic volatility estimation with PyMC3 and probabilistic programming. Chapter 11 covers decision trees and random forests for a long-short strategy on Japanese stocks, including rule extraction, interpreting results, and ensemble advantages. Chapter 12 explains gradient boosting, a tree-based ensemble that improves over random forests by reweighting data. It explores scikit-learn, XGBoost, LightGBM, and CatBoost implementations, SHAP interpretability, and high-frequency strategy design. Chapter 13 covers dimensionality reduction and clustering techniques for unsupervised learning, PCA, ICA, SNET, UMAP, CMEANS, hierarchical, and in-situ-based methods, to identify data-driven risk factors, e.g. portfolios, and build robust portfolios with hierarchical risk parity. Part 3. Natural language processing for trading. Chapter 14 explains how to convert text into a numerical format using token counts and a document term matrix. It introduces the naive Bayes algorithm, compares it to linear and tree-based models, and demonstrates sentiment analysis on financial news or earnings transcripts. Chapter 15 discusses topic modeling to extract hidden themes from large collections of financial documents. It covers latent semantic indexing, probabilistic latent semantic analysis, latent Dirichlet allocation, scikit-learn and Jensen implementations, and uses for sentiment or thematic indicators. Chapter 16 covers word embeddings, using neural networks such as Word2Vec, Doc2Vec, and transformer-based BERT models. It explains how to train, evaluate, and fine-tune embeddings on SEC filings to predict stock price moves or sentiment signals. Part 4. Deep and Reinforcement Learning. Chapter 17 introduces feed-forward neural networks and training them with backpropagation, regularization, and tuning. It examines TensorFlow 2.0 and PyTorch, architecture design, and how to build a deep neural network that generates trading signals for backtesting. Chapter 18 explains convolutional neural networks for time series formatted as images and for satellite imagery. It covers transfer learning, imagery-style feature extraction, and how to build a strategy that uses CNN-based return predictions or classify economic activity from satellite data. Chapter 19 discusses recurrent neural networks, particularly LSTM and GRU architectures, for univariate or multivariate time series forecasting, sentiment analysis, and bidirectional sequences. It shows how to train RNNs with pre-trained word embeddings for stock return prediction. Chapter 20 covers autoencoders, a type of unsupervised neural network that learns a compact representation of input data. It explains how to build and train autoencoders to extract risk factors and construct an asset pricing model that conditions on equity characteristics. Chapter 21 examines generative adversarial networks, training a generator and a discriminator in competition to produce synthetic financial data. It demonstrates how to use GANs for synthetic time series expansion, useful for training models or expanding backtest inputs. Chapter 22 describes deep reinforcement learning, defining Markov decision processes, value and policy iteration, clearing, and implementing a deep clearing agent. It highlights how to use the OpenAI Gym to create custom market environments and train RL agents to trade stocks. Chapter 23 summarizes the key tools, applications, and lessons learned. It outlines next steps for expanding machine learning techniques and daily use, incorporating new data sources, or exploring advanced models. Chapter 24 presents the Alpha Factor Library, detailing how to compute technical indicators with TALibs, implement formulaic alphas from the World Quant paper, and evaluate predictive quality with rank correlation, mutual information, SHAP values, and alphalins.